Hey everybody, Dr. A here, and in this video we're going to be providing some background information and some derivations related to work and energy for flexure members. So let's go ahead and get started. First, we want to recall that work done on a body is transformed to internal work. Now, internal work is also called strain energy, and we've talked about this before in some previous videos. Now, what do we know about the conservation of energy? Well, we know from physics that external work done on a body is going to be converted to internal work that is within the body itself. Okay, so we should know that from before. Now, for flexure members and systems, remember these are systems like beams and frames that are subject to bending. They would tend to flex. So for these kinds of systems, the internal work is derived from primarily bending, which is caused by the internal moment M. Okay, so let's do this. Let's write this down. I want us to consider a moment that is going to rotate through an angle d theta. Okay, so let's go ahead and sketch here some angle. Okay, and I'm going to call this angle right here of rotation d theta. And let's say that I have a moment in that direction that's rotating through that d theta, okay? So what will that tell us? What is the work done from a moment? Well, remember the basic definition of work or even energy from physics. It was a force times a displacement in the direction of the force. That was work done by a force. Here we're dealing with work done by what? By a moment, okay? So here what we're going to have is the differential external work, dWEXT, is going to be equal to that moment times d theta. Here you've got the work done by a moment is moment multiplied by the angle that it is rotating through. In this case, it's a little differential angle d theta. Now, we can graph this and say that for linear elastic behavior, what would we have here? Well, we're going to plot this relationship. It's going to look something like this. We're going to have moment on the vertical axis and theta on the horizontal axis. And for linear elastic behavior specifically, you'll have this linear segment here. And let's say that you gradually increase the moment as you're rotating through this angle theta, all right? And you increase the moment to a value of little m, and that's going to correspond with a value of little phi. So this equation of this line is going to be m as a function of theta is little m over phi times theta. Okay, so this is function notation where theta is the independent variable and m is the dependent variable. Have we seen something like this before? Yeah, definitely. We saw something like this in a previous video, but with a force directed along a line, okay? Now, what I can do is I can perform some integration and I can find the area beneath this curve or beneath this linear segment, and that will get me this external work. So really, I'm just integrating both sides of this equation. This is a separable differential equation. So I could put an integral on both sides and find what W external is. So let's go ahead and write that. I'm going to say WEXT is going to be the integral from 0 to phi of m as a function of theta d theta. Well, do I know m as a function of theta? Absolutely. It's this equation right here when we said we increase m to a final value of little m that has a corresponding value of phi, okay? So I can substitute that in here. I can get external work is equal to the integral from 0 to phi of m over phi theta d theta, okay? And so then what does that come out to be? I'm going to write this here, WEXT. You raise it a power and divide by a new power. It's just the integral of a line, or it's the area of that triangle, right? The area beneath this linear segment, which is just a triangle. So if I evaluate this, I should just get m phi over 2, right? 1/2 times base times height, all right? And this is an expression for external work done by a moment rotating through an angle. Now, if you want to brush up on your integration, maybe pause the video and make sure you can evaluate this integral and you get to this same value, okay? Now, this is external work. We said external work is then going to get converted to internal work. So let's turn the page and let's look at what we've already drawn out for us. Internal work is developed as the material strains, okay? So let's consider that we have a beam segment here, and the beam has some kind of arbitrary loading on it, W, and, I put some restraints here, pin connection and roller connection. It doesn't have to be a simply supported beam. I just drew this for an illustration purpose. And let's say that I'm looking at this little element right here, dx, okay? And this little element, this blue element, dx, is located at a distance x away from this left support. So maybe pause the video and sketch this out right now. The next thing I want to talk about is I want us to zoom in on this little element dx and come over here and blow it up and look at it bigger, okay? So let's take this element dx, okay? Its width, its horizontal width is dx, and I'm going to call this the undeformed element. This is the element before W is acting on the beam. So this is like a beam just hanging out there without any applied load for now, okay? So the width is dx, and I'm also going to consider an arc length of ds, but again, this is before loading at this point, so that means that the arc length ds is equal to the element width dx, okay? ds and dx are the same thing, and I'm going to say that arc length is a distance of y above the centroid, okay? So I went ahead and I just kind of sketched the width dx based on this neutral axis or this centroidal location. Now let's apply the load, okay? So W is applied, and this beam is going to tend to bend or flex, right? It's going to bend or flex. So now I'm going to pull out that deformed element, and that's what I have down here, okay? This element down here is the deformed element, and I also noted ds and dx are not equal to each other in this deformed element. Now, we're still going to have that distance y here, all right? That's going to be the distance from the deformed neutral axis, that's this dx, to this arc length ds, that's a little distance above it. And when you apply this load to the original beam up here, you develop these internal moments. We know how to get those internal moments from our knowledge of internal loading, okay? So what else develops here? Well, what I'm doing here is I'm projecting these deformed planes on the edge of the element up to this common point O up here, okay? And I'm going to do this to help me derive some of these relationships. Now, it turns out that we're going to call this angle right here d theta, okay? That's going to be the d theta that we're interested in. And again, this is the angle that is the interior angle of this point O that's formed by projecting these deformed planes up to a common point, okay? Now, we can also specify a curvature or a radius of curvature with this figure as well. So it turns out that the radius of curvature is measured from that point O, to your neutral axis, and we can call that rho. All right, so this is radius of curvature, okay? Now, here's what I'm going to do next. The next thing I'm going to do is I'm going to look at a little area element in the cross section of this beam, okay? So I'm going to look inside of this cross section, all right, inside of the beam's cross section. And when I look inside of it, I see this kind of shape right here. Let's say that that beam is a rectangle, and you see this is like a 3D view here. Here's my neutral axis. Here's that same distance y above the neutral axis. And I'm going to extract this little differential element dA, okay? So it turns out that we can get a differential force on that element that looks just like this. We can say, hey, we are going to have this force here. I'm going to draw it in purple here, dF sub x, acting on that differential element, okay? And so what is that? I'm going to come right here in the middle now. I'm going to say dF sub x, that differential force on that element is going to be equal to the stress, sigma sub x, on that element times the differential element, the differential area element itself, dA. Now, I can break this dA down into a dx, a dy and a dz here, okay? So remember, this is an area. It's going to have a dimension dy and dz. So I can break that down as well. I can say dfx equals sigma x times dy dz, all right? Now, what we're writing here is we're saying, hey, this internal moment, which again is right here, acting in this cross section is going to be somehow resolved into a single force acting on a little differential element. So if you want it to be a little bit more proper, you can put that same m right there going about the neutral axis of the cross section. And again, it's resolved into a little differential force dF on that element, okay? So now what I can do is I can piece this together, piece this theory together using Hooke's law and the flexure formula, okay? So you remind me, what does Hooke's law tell us? Well, Hooke's law says that sigma, which is stress in a particular direction, I'm going to call this sigma x because that's what I called it on the previous page, is equal to modulus of elasticity times strain, okay? And then the flexure formula from mechanics of materials says sigma x equals my over I. So I can utilize these two and put this together with these relationships to build out my internal work theory. Okay, so it turns out, let's write this down, turns out that the differential internal work is going to be equal to 1/2 times dF sub x times a little differential deformation d delta sub x, okay? Now, what is d delta sub x going to be? That's an elongation of some sort, okay? So this is going to be an elongation or a deformation at this area location, all right? So what can how can I express d delta x? Well, that's just strain epsilon x times dx. How do I know that? Well, this is just the definition of strain. I just rearranged it, right? Strain is a deformation divided by an original length, but this is the differential form of that, okay? So I can piece all of this together, and I can say dw internal is equal to 1/2 dF sub x times epsilon sub x dx. Well, remind me, what is dF sub x? What is this dF sub x? Well, we did this on the previous page. It is sigma x dy dz, right? So I can substitute that in, and I can say, okay, this is 1/2 times sigma x dy dz, and then again times epsilon x dx. Okay, now I can start kind of reimagining things. Well, what is dy, dz, dx? If I multiply these three differentials together, that just gives me a volume, doesn't it? So I could easily rewrite this as W internal work is equal to 1/2 sigma x times epsilon x dV for volume, okay? Again, you're multiplying three differential dimensions here, dy, dz, dx, to get you a differential volume. Now what I can do is piece all of this together and then take the integral, because this is still a differential equation, right? This is still a differential equation, and we've already separated it. We've already separated it in as a separable differential equation. So I can say W int equals the integral over that volume of sigma x epsilon x over 2 dV. I just took the integral of both sides of this separable differential equation, okay? Now, where I'm going to use Hooke's law and the Flexure formula, I'm going to substitute these two relationships in here strategically, okay? So at this point, I'm just going to do some algebra. Watch this. I can rewrite this as the integral over that volume again, okay, of sigma x squared over 2e dV, okay? So maybe pause the video, make these substitutions in here strategically, okay? And specifically, I want you to look at this one first. Look at Hooke's law and see how you can incorporate that in here to get this next term that we just got, okay? Now, we're going to strategically substitute the Flexure formula in somehow, okay? How am I going to do that? How am I going to substitute that Flexure formula in here? Well, sigma x is right here, so I can substitute my over I in for sigma x now, right? So I can say this is equal to the integral over that volume of 1 over 2e. I just kind of lumped those constants together, of my over I squared d volume, okay? Now, I can reimagine d volume as what? I can reimagine it as dA times dx. So watch what I can do now. I can say WINT equals the integral from 0 to a length L of m squared over 2ei squared, and then inside of that have the integral over the area, that area element, y squared dA squared dx. So I did two things here. Here I broke this d volume into a dA dx, and then I also did a little bit more algebra to repackage something unique that's going on here. So here's what I want you to do. I want you to pause the video and see if you can follow along from this step to this step on your own. Show your own algebra to convince yourself of it, okay? And then finally, what I can do is, what does this term represent for us? Well, that's just a moment of inertia term, okay? That's I. That's a moment of inertia term that we have learned about in a statics class. And we already have an I squared here, so we can actually cancel one of these i's in this denominator where it says I squared, all right? And then we can lump this together and simplify it. So what I'll finally get, if I rewrite this really nicely, is the internal work is going to be equal to the integral from 0 throughout the length of the beam segment of m squared over 2ei dx, where I is the moment of inertia about the bending axis, and E is a modulus of elasticity value, and M is the internal moment, okay? And so this is our reimagined and derived internal work formula. Now, The purpose of this video is to help us understand the derivation of this idea of work and energy caused by a moment. Now, when do we use this? Well, we use this as the basis to develop the virtual work method and Castigliano's method to perform more tangible analyses. Okay, so let's make a comment here. We're going to say we use this theory to develop the following two: the method of virtual work and Castigliano's method for flexure systems. Okay, for flexure systems, which again are like beams and frames. Okay, so that concludes this background and derivation video. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.